Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is Module 13 in our Circuits to Lecture series, where I talk about frequency-dependent transfer functions and filters. So when we were working through the Laplace transforms section of this lecture series, we spent a lot of time talking about transfer functions. And we had an input signal and an output signal and a transfer function. And we multiplied the transfer function by the input, and that allowed us to get the output signal in the Laplace domain. We are going to basically extend that idea and start working with transfer functions in the frequency domain. And so I've got a picture of the transfer function here, and this will look very, I think, reminiscent of what we talked about with the Laplace transforms, except now our signal, our input signal x, our output signal y, and our transfer function are a function of omega frequency rather than s. And just like the Laplace transform, or for the Laplace transforms, our system transfer function is defined as our output signal divided by our input signal. And for this class, our input signal x will always be a sinusoid. So it will have some amplitude, an angular frequency omega, and a phase shift. Now, we are going to look at a single sinusoid oscillating at a particular frequency omega for our discussion. But in general, a signal can be made up of a range of frequencies. And that's what Fourier analysis is all about, showing how you can construct an audio signal or a wireless communication signal from a sum of sinusoids. And so when we analyze our frequency-dependent transfer functions for a single value of omega, the same transfer function can be used for input signals that are made up of a summation of many different sinusoids. So this is a very general purpose analysis that we're going to be talking about. And since our signals, for our purposes, are going to be single frequency sinusoids, we can represent them using phasors. And so our input signal, x of omega, I will often write as just a bold x, which we will recognize as a complex signal with a certain magnitude AI and a certain phase shift phi I. And our output, similarly, will be a bold y, which is, again, a complex phasor with a certain magnitude and a certain phase. And just like when we were working with our Laplace transforms, the transfer function that we're going to be interested in when we look at our frequency-dependent circuits or filters will be the voltage transfer function. And so we can draw our system. And we would consider it a two-terminal input. Here I just wrote, I just showed one input in kind of a generic way, but to be very specific, we're going to be considering voltage gains. So our input voltage will be represented as VI, our output voltage as VO, and our frequency domain transfer function, or frequency-dependent transfer function, is just V out over V in. So basically exactly the same as when we were working with Laplace transforms, except now, rather than signals that have been Laplace transformed in to the S domain, we're dealing with phasors, right? So our input voltage will be a sinusoid with a certain amplitude and phase represented by a phasor VI, and our output will also be a sinusoid with a certain amplitude and phase. And so these two are complex numbers. So in general, the voltage transfer function h of omega is also complex because it's a ratio of two complex numbers, and the value of that complex numbered, or the value of that complex transfer function, is going to change as omega changes. So by far the most common application of circuits that have a frequency-dependent transfer function is filtering. And a filter is basically just a circuit that blocks signals at some frequencies but allows signals at other frequencies to pass through. And there's a few different kinds of ideal filters, and the reason why I'm calling them ideal filters is I'm going to show you a transfer function response that is extremely sort of sharp. In reality, we cannot construct signals that have this kind of very sharp transfer function, but it's a useful way to introduce the concept. So let's start out with a low-pass filter. And on this graph, I'm going to plot the magnitude of our frequency domain transfer function versus omega, which is the frequency in radians per second. And a low-pass filter, basically for frequencies that start from 0 and go all the way up to some frequency omega c, this low-pass filter will basically allow all of these frequencies to pass through unchanged. So the magnitude of the transfer function is 1. So the magnitude of the output voltage is equal to the magnitude of the input voltage. But once we hit omega c, the response of our filter, or the magnitude of our transfer function, drops down to 0. And we call this the cutoff frequency. And so this is what's known as the pass band. And this is what's known as the stop band. So basically we could take a sinusoid, feed it into our filter circuit, and as long as the oscillation frequency of our sinusoid omega was below our cutoff frequency, our sinusoid would pass through basically unchanged, possibly with a phase shift. But once we hit omega c, then all of those signals are blocked. As you might expect, there are different variations of these filter circuits. So, for example, we can also have a high-pass filter. It also has a cutoff frequency, omega c, but it has sort of the inverse response of the low-pass filter. So for any signals that have a frequency of omega c or greater, the circuit passes them through unchanged. Again, this is the magnitude of our transfer function. And any sinusoids that have frequencies between 0 and omega c, those sinusoids are completely blocked, right? So the response of our filter here is 0. And this is a low-pass filter because it passes the low frequencies, a high-pass filter because it passes the high frequencies. So there are two more types of filters. The next one is what we call a band-pass filter. And so we have two frequencies. Let's call them omega 1 and omega 2. And the filter response for a bandpass filter is equal to 1 between omega 1 and omega 2, and it's 0 outside. So this range of frequencies is the passband of the filter, and above omega 2 and below omega 1, those are the stop bands of the filter. Finally, we also have a band stop filter. It also has a couple frequencies, omega 1 and omega 2. And basically the stop band for the band stop filter is between omega 1 and omega 2, so the response here is 0. And the response is 1 below omega 1, and the response is 1 above omega 2. And band stop filters are also sometimes known as notch filters. And bandpass filters, of course, get their name because they allow a band of frequencies to pass through, but they stop everything else. And in the phasor sinusoidal analysis review module that I hope you've watched, and if you haven't watched it, please check out that module before you go any further in this one. In that phasor analysis review module, we presented this circuit, this now very familiar RC circuit, and we used complex impedances to determine the output phasor voltage across the capacitor in terms of the input phasor voltage across this terminal here. And using that analysis, we saw that the output voltage is equal to 1 over j omega RC plus 1 times V in. And so in other words, our frequency-dependent transfer function, V out over V in, is equal to 1 over j omega RC plus 1. And in the review module, I did talk about what happens when we change the value of omega. So for example, at very low frequencies, let's say when omega is equal to 0, this term goes to 0, and we then just have 1 over 0 plus 1, or in other words, 1. So our voltage transfer function for low frequencies is equal to 1. However, when we consider very high frequencies, let's say omega equal to infinity, we have 1 over infinity, basically, which is equal to 0. And so our voltage transfer function is very small, or 0, for very large frequencies. So this circuit, because of this transfer function, basically has a characteristic that allows lower frequency sinusoids to pass, but blocks higher frequency sinusoids. And sure enough, this is our very first filter circuit, and this particular one is a low-pass filter. And we can confirm our, sort of our intuition here by looking at a simulation of this circuit, both in SPICE and in MATLAB. Okay, I'm going to show you basically two different ways to simulate the response of that low-pass filter circuit that I showed you just now. The first one is using SPICE, and so this is the SPICE file that I will post. And to do a frequency domain plot, or a response of the frequency dependent, or sorry, a plot of the frequency a plot of the frequency dependent response of the low pass filter, we have to use something called AC analysis in SPICE. And so we define our voltage source just like we have in the past. It's connected to node 1 and node 0. However, rather than DC, which we've used a few different times, or pulse or PWL, we now use the two letters AC, and this is just the amplitude of our source. we have a 1K resistor going from node 1 to node 2, and then going from node 2 to ground, we have a 1 microfarad capacitor. In our control section, we are going to ask SPICE to do an AC analysis to go up using decades of frequency. We're going to have 10 points per decade, and a decade is just a power of 10. We're going to start at 1 hertz, and we're going to go all the way up to 10 kilohertz. We're going to plot the magnitude of our voltage, and we're going to do it on a log x axis. And so if we run it, it looks like this. And sure enough, we do have a low-pass filter response. So for low frequencies, we have a response that's basically equal to 1, as we suggested just looking at the equation. However, as our frequency increases, rather than having this very sort of sudden sharp drop like we had when I was showing you those ideal filters, instead, most practical circuits will have kind of a gradual roll off. And so we roll off here, down, and then eventually we get very close to 0. Often the y-axis will be shown in decibels rather than linear, but this particular plot is just linear. And the question is, with this very gradual sort of roll off, where do we define our cutoff frequency? And usually it is at the point where we drop 3 dB from our maximum, and 3 dB is about a factor of 2. So in a linear scale, it would be at 0.5. So the cutoff frequency would be about 200 hertz in this particular case. So I'm going to close that, and now I'm going to show you also the MATLAB file. And so in the MATLAB file, we're going to plot in terms of F rather than omega. And that's just so we can compare to the SPICE plot, because the SPICE plot is also in terms of F and not in omega. And so we're going to go from 0 to 100 kilohertz. And we've got a resistance of 1 kilo ohm, a capacitance of 1 microfarad. And then what we're doing here is I'm basically just I'm just calculating the magnitude of the equation for the frequency response. And so we've got J times, I'll just surround this with a bracket, 2 pi f, which is of course equal to omega, times r times c plus 1. We're then plotting the magnitude versus frequency, and I'm labeling, the x and y axes, and I'm turning on the grid. Now I should point out that, even though I'm calling this a simulation, that's maybe not really the right term. This is just kind of a plot of the equation that we got from our circuit analysis. So this is a very different program than SPICE. SPICE will actually simulate the circuit elements using models for the circuit elements, and all we're really doing in MATLAB is we're plotting the equation that we came up with in our analysis. And that's not what SPICE does. SPICE does something a little bit more detailed. But if we run this and we look at our plot and we compare it to the SPICE, it's going to be exactly the same result. So for a value of 0.5, we're at about a cutoff frequency of 200 hertz, and we see the same kind of gradual drop. So the result is the same, but we're really sort of fundamentally doing two different things. And this is really, again, highlighting the advantage of working with both SPICE and MATLAB, because if we make a mistake with our circuit analysis, that mistake is going to continue on to our MATLAB plot, because we're just going to plot essentially the equation that we came up with from our analysis. But SPICE is a completely different thing. It doesn't ask for our equations. It's not interested. It just wants the topology of our circuit. And so it's really useful to use SPICE as a check to make sure that our analysis is correct. So I'm going to conclude our discussions of filters, or wrap up our discussions of filters, by talking about passive filter structures. And we call them passive filters because they contain only resistors, capacitors, and inductors. So no elements that can add energy to the circuit. There are active filters, and active filters contain things like op amps or other transistor structures that can not only filter but also potentially amplify or at least overcome circuit losses. But we're going to stick to passive filters for the purposes of our discussions. And the first two filter classes, the low pass filter and the high pass filter that we're going to be looking at, have this basic structure. So we have an element with impedance Z1 in series with our input, and then an element with impedance Z2 in parallel with our output. And our output voltage then is just equal to, using the voltage divider rule, equal to Z2 over Z1 plus Z2 multiplied by the input. And so this is going to be the standard formula that we use to determine the transfer functions of our high pass filter and low pass filter structures. And we'll look at a total of 4 structures that all sort of use this general form. And if you're unsure about, again, complex impedance, or just using the voltage divider rule in this way, please check out the phasor analysis review module. So there are actually 2 ways that we can use passive elements to design a simple low-pass filter. The first one is our familiar circuit, our familiar RC circuit that we've been talking about up until now. The second one is new. The second one has an inductor in parallel with the input and then a resistor in parallel with the output. And what I'm going to do is use the voltage divider equation that we had on the previous page to determine the transfer function for both of these structures. And so in this structure, our impedance Z1 is equal to R, our impedance Z2 is equal to 1 over j omega c, and over here our impedance Z1 is equal to j omega L, and Z2 is equal to R. And so the output voltage for the RC circuit is equal to 1 over j omega c over R plus j omega c times the input. And if we multiply the top and bottom by j omega c, and then we take the ratio of V out over V in, we get 1 over j omega RC plus 1. And that's the result that we had before. Over here, we have V out is equal to R over j omega L plus R times the input. And if I multiply the top and bottom by 1 over R and take the ratio of V out over V in, the transfer function over here is equal to one over j omega L over R plus 1. So both transfer functions have exactly the same form. We've got 1 on the top and a j omega plus 1 term on the bottom. The only thing that's different is this is R times C and this is L divided by R. This, as we're going to see later on, this determines the cutoff frequency, the value of L and R, the ratio of L and R, and the product of R and C. And so you just have to choose your component values accordingly to pick the cutoff frequency that you want. And in the next module, we're going to talk about something called Bode plots. And as part of that module, we're going to look at a way of estimating the cutoff frequency. And so what are the applications of low-pass filters? Well, generally they are used to remove high-frequency noise. In other words, if we look at our signal in the frequency domain, often, let's say we're dealing with an audio signal, for example, the audio signal will exist over a range of frequencies, and after a while, those frequencies will taper off. So once we sort of get up to the maximum frequency that the human ear can hear, there's no point, unless we have some kind of ultrasound application, there's no point generating signal components that are higher than, sort of what the human ear can register. And so this could be our signal. And in some cases, this is a little lower than what the human ear can register, depending on the application. However, often the signal will be corrupted by noise that has low frequency components, but also very, very high frequency components. And this noise can come from the thermal noise of our electronics, just kind of random electrons bumping around, or if we're using some sort of digital to analog converter that has some quantization, this noise could be caused by the signal quantization. And for some applications, for things like voice applications, for example, if our signal cuts off, a little bit before the cutoff of the range of frequencies that our ear can hear, this high frequency noise can sometimes cause kind of a ringing or a buzzing. And so one application of a low-pass filter is to design a low-pass filter with a cutoff that basically follows the contour of our desired signal. So this would be our low-pass filter. And then we pass the desired signal and we remove any high-frequency noise that's in the stop band of our low-pass filter. And of course, there's nothing we can do about the noise that's corrupting our signal within the signal band, but we can get rid of this noise that's outside of our signal band. And this is a very, very common application for low-pass filters. The next filter structure we have is the high-pass filter. And just like for the low-pass filter, there's actually two ways to create high-pass filters. The first one we've already seen. So this is the RC circuit where we switch the location of the capacitor and the resistor. And over here, this is where we make a high-pass filter with the inductor resistor circuit. And just like we did for the capacitor and resistor, we just switch the locations of the inductor and the resistor. And so in this circuit, Z1 is equal to 1 over j omega c. Z2 is equal to R. And so our transfer function is equal to R over 1 over j omega c plus R, or j omega RC over j omega RC plus 1. And this was the same transfer function that we saw in our review module. And basically, when omega is very low or when omega is equal to 0, this response is equal to 0. And when omega is equal to infinity or very high frequencies, this transfer function is approximately equal to 1. Over here, we have Z1 is equal to j omega L, and Z1 is equal to R. Z2 is equal to j omega L. H omega then is equal to j omega L over j omega L plus R. And then if we multiply the top and bottom by 1 over R, we have j omega L over R over j omega L over R plus 1. Same form as the RC, just the components are different. And again, the cutoff frequency of these filters are determined by the RC product in the case of the left-hand filter and the ratio of L over R in the case of the right-hand filter. And we'll talk more about that in the next module. One application of a high-pass filter is removing the DC offset of a signal. And so, for example, let's say we have really, maybe just a sinusoid. That has a certain DC offset. If we pass this through a high-pass filter, the DC offset of a signal is basically its frequency component at omega equal to 0. And so if we block that, what we end up doing is removing that DC offset. So our signal will look like that. And of course, our high-pass filters are not perfect. And so if this was a very low frequency sinusoid, the filter would probably block some of the sinusoid itself. But as long as the frequency of oscillation of this sinusoid is above the cutoff frequency, the DC offset for sure is below the cutoff frequency, and the sinusoid basically passes through and it looks like it's been completely unchanged other than being translated downwards. And one of the places that you want to do this, and we'll do this in our class project, is when you're driving a speaker. So generally speaking, you don't want to have a DC offset when driving a speaker because it wastes energy, basically. A DC offset just will sort of give the speaker an actual physical offset, and then it'll still sort of vibrate and make sound, but you're kind of wasting power. And this, creating signals with a DC offset typically happens when you're working with a digital to analog converter that's powered with a positive voltage and ground. And so because that digital to analog converter only has positive voltages to work with, it will only generate signals with a DC offset. And so you can then put a high-pass filter in series with your digital to analog converter in your speaker and remove that DC offset. Okay, the next structure, and this structure has 3 elements now rather than just 2, is the bandpass filter. And so the bandpass filter has an inductor and a capacitor in series with the input, and then a resistor in parallel with the output. And we're still going to use the voltage divider rule, even though we've got 3 elements. So the inductor will be Z1, the capacitor will be Z2, the resistor will be Z3. The output is equal to Z3 over Z1 plus Z2 plus Z3 times the input. Or in other words, R over J omega L plus 1 over J omega C plus R. Or the transfer function if we want to, group terms, I guess, just a little bit. J times omega L plus 1 over omega C. And so how is this a bandpass filter? Well, basically, when we've got an input sinusoid that's very low frequency, the capacitor is going to block it because a capacitor looks like an open circuit at very low frequencies. If we've got a sinusoid with an input sinusoid with very high frequency of oscillation, the inductor is going to block it because the inductor looks like an open circuit at high frequencies. And if we're somewhere in the middle, then the inductor and the capacitor will allow the signal to travel through. And what's an application of a bandpass filter? Oops. Application. But an application is filtering a wireless signal. Often, when we look at a wireless signal in the frequency domain, the wireless signal is not centered around 0, but in fact has been shifted up to be centered around something we call the carrier frequency. So omega c we would call the carrier frequency. And the reason for this is just because the electronics of a wireless transmitter, things like antenna size and stuff like that, are easier to implement when we're dealing with higher frequency signals. And so we'll take a low frequency signal, multiply it by a sinusoid, which shifts it up into the high frequency. And so if we took a frequency domain snapshot of a wireless signal flying through the air, it would look something like this. And so similar to the kind of audio example that I had when we were talking about the low-pass filter, wireless signals are also subject to a very broadband noise. So this is our signal. This is our noise. And as our signal is being received, we want to basically cut down on the amount of noise that we're letting into our system. And so we would design a bandpass filter such that its passband followed exactly the shape of our signal, and then we would cancel out the noise that is at the higher frequencies and at the lower frequencies. And so our last filter type is the band stop filter. We have our input voltage and our output voltage as before. Z1 is the resistance, Z2 is the inductance, and Z3 is the capacitance. Using the voltage divider rule, the output voltage is Z2 plus Z3 divided by Z1 plus Z2 plus Z3 times the input. And if we substitute in our impedance values and take the ratio of the output voltage to the input voltage, we get J times omega L plus 1 over omega C divided by R plus J times omega L plus 1 over omega C. And how is this filter working? Well, basically, we now have the inductor and capacitor basically forming a path to ground. And at very low frequencies, the capacitor is an open circuit, and so there's no path to ground, and so our sinusoid will pass through to the output unchanged. At very high frequencies, the inductor is an open circuit, so again the signal can't flow to ground, so it flows through to the output unchanged. But at intermediate frequencies, both the inductor and the capacitor will conduct, forming a path to ground, and so the intermediate frequencies are shorted to ground and as a result do not pass to the output. And what's the application? Well, often it's to remove narrowband interference. And so let's say you've got an audio application your signal looks like this. And for some reason you have, an unwanted interfering signal that is very narrow, sort of right in the middle of your signal. And an example of this might be, 60 hertz buzz in, an audio amplifier or something like that. You can sort of hear that kind of power line type buzzing in your equipment. And one of the ways you could get rid of that is to introduce a band stop filter with a response like that. It would basically notch out the interfering signal. Now, we'll also potentially notch out your desired signal as well, so you might have to sort of be careful with the design, but that's sort of something that is a typical application of a band stop. And so this kind of concludes our discussion of passive filters. There's just a few one point I'd like to conclude on. At the start, I mentioned that there is such a thing as active filters with transistors and op amps and stuff like that. And it's also possible to create filters that consist of a larger number of resistors, capacitors, and inductors. And those filters we refer to as higher order filters. So for example, you can create a low pass filter with a number of resistors and capacitors and inductors even. And the advantage of incorporating more components into your circuit is that you can make a filter with a sharper cutoff. When we looked at our simulated results, it seemed like our signal was fairly, had a fairly gradual cutoff. And particularly for an application like this, for example, we would want to have a very narrow, sharp cutoff that was just around our interference and nowhere else. And so if you want a sharper cutoff, you add more components to your circuit, basically. And so this creates second, third, fourth, fifth order filters. And the design of these filters is, there's a rich body of theory around the design of these filters, if that's something that you're interested in looking at. But that's beyond the scope of this kind of Circuits 2 lecture series that we're doing.